Reversibility is one of the most basic, most fundamental microscopic physical law of nature. Here, I consider a problem of composing computers, reversible computers, in a reversible and conservative environment. Outline of the talk is as follows. A reversible elementary triangular partitioned cellular automaton, ETPCA in short, number 0157 is studied. In this cellular space, the shape of a cell is equilateral triangle, and it is further divided into 3 parts. And it has a very simple local transition rule like this. Okay. It is an abstract model of a reversible physical world having a kind of conservation law. Here, a number of dots, particles, is conserved even if we apply such local transition rules. A reversible logic element with memory, RLEM in short, number 431 is composed in its cellular space. Here, 4 stands for 4 input and 4 output logic element, and 31 is its ID number. Reversible Turing machines, RTMs, are systematically constructed using RLEM 431. A pathway from reversible and conservative microscopic law to reversible computers is depicted in this figure. In the bottom level, a reversible microscopic law of evolution exists. From such a simple law, useful phenomena in the reversible cellular space are found. Using such phenomena, a reversible logic element with memory, RLEM, is composed. And then functional modules composed of RLEMs are designed. Finally, by assembling these modules, reversible Turing machines are constructed. In such a hierarchical way, even from such simple local function, we can compose complex reversible Turing machine. Past results are as follows. In other ETPCAs, number 0347 and 0137, RLEM 431 is simulated. By this, reversible Turing machines are realized in them very concisely. In ETPCA 0157, we are now investigating in this talk, Friedkin gate, a universal reversible logic gate, is simulated 21 years ago. But if we use reversible gates, construction of reversible Turing machine becomes very complicated. Here, we show that in this ETPCA 0157, RLEM 431 is simulated. And using this element, rather than reversible logic gate, construction of RTMs is greatly simplified. Reversible logic element with memory, RLEM, is a reversible sequential machine. a kind of a finite automaton having input and output symbols. From the present state P and the input AI, it determines the next state Q and the output Sj. In this element, input signal interacts with the state. Therefore, there is no need of synchronizing many signals, as in the reversible logic gates. Here we use a specific RLM number 431. It is described by such a move table, but we use this figure to represent its behavior, movement. There are solid lines and dotted lines. They represent input-output relation. If a signal or particle goes through the solid line, then the state changes to the other. And if a particle or input signal goes through a dotted line, the state remains unchanged. For example, if a signal goes through a dotted line, then the state remains the same. If a signal goes through a solid line like this, then the state changes to the other. By using RLM431, reversible Turing machines can be composed in such a way. But today, I do not explain this circuit in detail. But anyway, there is a finite state control in the left part, and tape unit is the right part. By the way, universality of reversible logic element with memory is defined as follows. If any reversible sequential machine is simulated in a standard method described below by a circuit composed of it, then such an RLM is called universal. For example, rotary element is known to be a universal RLM with 4 input ports and 4 output ports. If we consider such a circuit composed of RLM 37, 3 input ports and 3 output ports, and ID number is 7. Then a rotary element is simulated by this circuit, namely every occurrence of rotary element is replaced by such a circuit. Therefore, RM37 is universal. As for universality of RLMs, the following is known. If it has 3 or more input-output lines, then it is universal. All such RLM is universal. Only 3 RLMs, RLM 23, 24, and 22 are non-universal. Hence, RLM 431 is also, of course, universal. It was an open problem whether RLM 217 is universal or not. Recently, Matthew Cook in Switzerland, in Zurich, solved this open problem with his student. Anyway, it is universal. Therefore, only these three two input to output elements are non-universal. It is a very interesting problem result, but Matthew Cook has not yet published this result. I cannot say its details. Anyway, non-universality and universality are all solved now. But it is not the end of the story. There is a further problem on two-state RLEM. Look at the weakest element, RLEM22. This is the weakest one among all two-state RLEMs. Okay? Can RLEM22 simulate reversible Turing machines, even though it is not universal? Surprisingly, the answer is yes. It is also solved by Matthew Cook. Of course, simulation method is non-standard one. The standard simulation method is like this, but of course, this is non-universal. Therefore, some non-standard simulation method is used. I was surprised and I was very shocked by its result, but it is a very ingenious construction method. But again, Matthew Cook has not yet published his method. This result I cannot explain now. But here, sorry. But here, I use a universal RLEM 431, and I will try to realize this element in ETPCA 0157, having only these 4 local transition rules. To do so, we need 3 kinds of gadgets to realize this element. They are signal transmission wire, signal crossing gadget, and flip-flop gadget. Okay, by using these gadgets, we will construct RLEM 431. First, signal transmission wire is something like this. I will show how it works by using the simulator later. Okay. Signal crossing gadget is constructed like this. Signals from X and Y are crossed by this gadget. Okay. The third one is a little bit complex flip-flop gadget. This is a flip-flop gadget. I will show it by using a simulator, Gori simulator. Sorry, not this one. Okay. I will show how flip-flop gadget work by using a cellular automaton simulator, Gori. There are many signal transmission wires. Here are signals, and signals go along the wire. Okay. For example, here is a signal crossing gadget. Okay. And two Y patterns, but rotated by 90 degrees, is here and here. Okay. 5 signals rotate around the left Y pattern. Okay, like this, showing that the flip-flop is in the state 0. Right Y pattern, there is no signal. Okay, and there are 2 bridge module patterns here and here. They are used for adjusting the phase of the rotating signals around Y patterns. And state change is performed by giving signals. Signals is now here. And by giving 5 signals to this pattern. Okay. Then this control signals interact with signals on the Y module, Y pattern. Then the signals moves to the first bridge. Okay. Then again, these control signals interacts with these signals and move. These signals move to the second bridge. Then finally, these 5 signals is transferred to the right one pattern. Okay, indicating that the state becomes 1 from state 0. Okay, the state change from the state 1 to 0 is similarly done. Okay. Okay. By using such a flip-flop, we can implement the element RLEM 431 in this way. But today I omit its detailed explanation. Anyway, 431 is realized in such a configuration. This is an example of an RTM, reversible Turing machine, composed of RLEM 431. By replacing each occurrence of RLEM 431 by this pattern, we can obtain a complete configuration of a reversible Turing machine in the cellular space of ETBCA 0157. Okay. Okay. Again, I will use Gori to simulate how it works. This is a whole pattern of an example of a reversible Turing machine. Sorry. Here is a finite control in the left side, and here is a tape unit for it. And detailed explanation of this Turing machine, I omitted its explanation. But anyway, by giving 5 signals to the begin port, like this, it starts to compute, okay? And if it is accepted, the input is accepted, then these 5 signals move to this accept port, okay? These 2 signals are for controlling the 5 signals. At first, no set of 5 signals is on neither on accept nor reject port. Okay. Anyway, signal moves along these transmission lines, and access many RM431. But anyway, it takes about 5 million steps to have an answer. And therefore, I use a high-speed mode. Okay. It is 1 million, 2 million, 3 million, 4 million, and 5 million, almost 5 million. Okay. Then we can see there are 5 signals in the accept port. Therefore, we can see the input is accepted by this reversible Turing machine. Okay. In this study, reversible Turing machines are constructed in a hierarchical way, even in an extremely simple reversible ETPCA 0157 in this way. Okay. It is left for the future study to find supernatural computing methods in nature to make a computer in much simpler reversible environment. Thank you for your attention. That's all of my talk.
Thank you very much. So is there any questions or comments? We have a few minutes. Yes, please.
Then,
yes.
The number 5 particles is essential to encode a signal?
No, not at all.
Is it possible to reduce?
To reduce, for example, only 1 signal is okay. But if we do so, then timing adjustment becomes complicated. Okay. To make it easy to adjust signal timing, we use 5 signals. Further explanation will be very technical, therefore I omit its details.
May I ask why you use RM413s? So, for example, in your famous study, rotary elements are universal, and by using rotary elements, you can implement reversible Turing machines. So why rotary elements are not used in this work?
sorry, just wait a moment. I will. Uh, 431 has only 2 solid lines. Okay? On the other hand, rotary elements has 4 solid lines in total. Of course, rotary, we can implement rotary element in this cellular space, but to change the state from 0 to 1 and 1 to 0, it needs a very complex mechanism. Therefore, since this element has only 2 solid lines, it becomes easier. And also, reversible Turing machines can be composed of this element 431 relatively easily, like rotary element. Therefore, in this construction, we use RM431. Of course, it is possible to implement a rotary element, but it becomes very complex.
I see. So the number of elements is greatly reduced if you use this RM431.
Yes, yes. Number of element is also small, and configuration of implementing this element is also small.
Are there any other questions or comments? Okay. So thank you very much.
Thank you.